right, so now we'll talk about something that's called the linear combination of atomic orbitals. So we've seen already that we can write molecular orbitals, such as for hydrogen, as a sum or a difference of atomic orbitals. And so we're going to use throughout the class this idea of linear combination of atomic orbitals and writing molecular orbitals as a linear combination of atomic orbitals. So our atomic orbitals are going to be something that we often call a basis set. So in math in general, if we represent a function by a set of other functions, those functions can be called a basis set or basis functions. So for example, we might draw a position vector r. It might have basis functions x and y, and then we could draw any position vector r as being a linear combination of those. So for example, 3x minus y, we're writing it as this 3 times our x basis function minus 1 times our y basis function. So we can always use basis functions to represent some other function. And so in our case, what we're going to do is think about hydrogen-like atomic orbitals as our basis set. We know these are pretty good for a single atom. They can be used to solve the Schrodinger equation, for example, for hydrogen. But it turns out we can then use them to construct molecular orbitals. So we'll have a linear combination of atomic orbitals is how we're going to write the wave functions for our molecular orbitals. So we'll take our molecular orbital, so call it phi. This is going to be written as a sum of our basis functions. So we've got our basis function phi times a coefficient ai. And we'll have one coefficient for each atomic orbital. And then however many atomic orbitals we have is n, that's our number of atomic orbitals. So keep this idea in mind, is that when we write our molecular orbitals, we're writing them as this linear combination. That means this sum of coefficient times a basis function. Now, we've talked again before about some linear molecules like H2 or N2. Now for nonlinear molecules like oxygen, we're not going to use sigma or pi to describe the orbitals. So we're going to end up using symmetry representations from the molecular point group. So when you see these kinds of representations, 2a1 or 1b2, those are representing the irreducible representations that come from a molecular point group. We're going to be labeling our orbitals in energy. So as we go up in energy, we're going to increase the labeling. Now we're going to label them by the irreducible representation. So for example, here we have 2a1, go up to 3a1. These are 4a1. They're all conveniently colored blue in this particular MO diagram. So we've got these 3 A1 representations, just the second one, third one, fourth one. The first one is really low in energy and is not shown here. Also on this diagram, there are some B2s. So we've got our 1b2 and our 2b2. And then if there were additional unoccupied orbitals, those would go up higher and higher in energy. We've got our 1b1 shown here, and so on. Now, when we think of water, we can think of this as, writing those molecular orbitals as something that comes from atomic orbitals of oxygen plus atomic orbitals of hydrogen, or from the molecular orbitals of H2, which is something that you may have learned about during group theory. So if you wanted to write the 2a1 orbital, which is shown down here, this is essentially something that comes from the 2s orbital of oxygen plus the sigma orbital of the H2 molecule, or alternatively, if you didn't want to write it as a molecular orbital, you could write it as the atomic orbitals, 1s of HA and 1s of HB. So basically, in the end, our molecular orbital is going to look like the 2s of oxygen plus the 1s of hydrogen A and the 1s of hydrogen B. So out of these molecular orbitals, some of them are very straightforward. So for example, the 1b1 shown here, this one is essentially 100% of the 2px orbital that comes from oxygen, if we only have one orbital per atomic orbital. Now others are more complicated. So if you were to look say it is 3A1, that one's a little more complicated. It seems to have some 2s contributions from the oxygen. It's got some 2pz contribution from the oxygen. And then it's also got this 1sHa and 1sHb types of contributions. So different orbitals have different amounts of this. So let's try to think about how we can represent this. So we've got our diagram. When we do a calculation, again, we're going to be using atomic orbitals or atomic orbital-like functions as our basis set. So in this particular case, for water, I'm using a basis set that has exactly 1 per atomic orbital. So we'll have something that looks like the 1s function of oxygen. This is a 2s function. So ignore those numbers a little bit. It doesn't quite mean dotted. This is talking about atom number 1. But this is our 1s function. That's our 2s function. This is a 2px, 2py, 2pz. We've got one of our hydrogen 1s functions and the other hydrogen 1s function. So this is our atomic orbitals. This entire column here represents one particular molecular orbital number 1. And all the numbers down here are part of the coefficient matrix. Remember those coefficients that are part of our linear combination of atomic orbitals. These are those coefficients that you multiply by the AO to give you the MO. So to read this coefficient matrix, what we can look at is we can look at this first coefficient, for example, and we can see that if we were to take the square of this, but if we take the square of that, that's essentially 1. All these other values are very small. So you can think of this first orbital as being essentially 100% the 1s orbital from oxygen, and it's really low in energy. When I mentioned the 1A1 was really low in energy, that's because it's this core orbital of oxygen. So that's our first molecular orbital. And again, this is something that a calculation can give you, is this coefficient matrix. All right, so that's our first MO. We can move on and look at our second molecular orbital. So again, taking a look at all the coefficients that show up. In this case, our highest coefficient is here. This is that 2s orbital of oxygen. That's our primary contribution, but it's not, of course, the only contribution. One thing to note is that we definitely have contributions from the 1s orbitals on the hydrogens, so that 1sa and 1sb. And again, they've got a plus sign. They've got the same phase as one another and the same phase as this 2s orbital. In this case, there's also a bit of a contribution from the 1s orbital on oxygen, a little bit of a contribution as well from the pz orbital on oxygen. Anything with the same symmetry is going to mix. The main contributions are that 2s and then those hydrogen 1s's that we'd think about. If we want to take a look at what this orbital would look like, here's a picture of this molecular orbital that represents essentially a density or a probability of finding an electron in a particular space. So our cartoon looked kind of like s electrons from the oxygen and the 2 hydrogens, but this is what the shape of the actual molecular orbital would look like. Moving on to our third molecular orbital, we can have now a slightly different symmetry for this. We can see in this case we've got a strong contribution from the py orbital on oxygen, oriented this direction. There's also some pretty strong contributions from the hydrogens. And in this case, we've got 1s orbitals on the hydrogens, but now we've got a plus and a minus. So we've got different signs. Again, with our cartoon, we can see that we've got 2 different signs for the 2 different hydrogens. And it lines up with our p orbital. If we wanted to get a picture of the molecular orbital that we get from our calculations, again, it's going to now look a lot like this cartoon, only the white part has kind of smeared out. You can see that you've got a lot of density on one side, you've got a lot of density on the other side. There is a node that goes in between the system, so there's 0 probability of finding electron density right in the middle. But overall, anyways, this picture looks a lot like the cartoon that we might have drawn. You can move up in in energy and start to get to this more complicated orbital. So I mentioned the 3A1 was reasonably complicated. So now if we look, we've got contributions from the PZ on oxygen and the 2S on oxygen. Those are both very strong contributions to this particular molecular orbital. Again, there's still some contribution from the 1S. There's also contributions from the 1s orbitals on the hydrogens. And again, this is a case where they both have the same signs. Our picture of this particular orbital, they've both got the same phase, same color. And so this is what our orbital looks like in our cartoon, what we'd expect. And then from games and visualize with McMullplot, we can get a picture of the orbital looking kind of like this. So all of the gray part here is smeared out to this region of electron density down here. We've also got electron density up there. Again, there's kind of a node going through our center of our molecule. We can keep going. So our fifth molecular orbital is pretty much 100%, in this case it is 100%, the 2px orbital on oxygen. If x is this direction. Rotated the molecule a little bit so that you can see that p orbital. But if you were to rotate the molecule this direction, you'd see we'd have it coming out at us and going away from us. So that's that orbital. And so we've now looked at all of the occupied orbitals that are in the water molecule. We can also do the same thing for the unoccupieds, but I won't walk through that. Again, we have coefficients for all of those orbitals. Again, by looking at that coefficient matrix, you can really determine what is that linear combination of atomic orbitals that builds up a molecular orbital. So again, just for comparison, we've got our little cartoon pictures of our MOs, and these are our actual calculated MOs that come out of a games calculation, and again, visualized with McMullplot. So we've got our different orbitals. Again, these are the virtual ones. Look a lot like the cartoons we might draw. But you can see too that there are some distortions here. It's trying to keep an anti-bonding here. Right here, it's drawing this perfect p orbital, but now you can start to see a little bit more of the distortions. So anyways, computational chemistry is very useful for being able to determine what molecular orbitals might look like, both the occupieds as well as some of the low-lying virtual orbitals. There's some caveats too, and we'll talk about those a little later in class. Anyhow, that's a lot about molecular orbitals of the water molecule.